Hi, today we will be doing an introduction to MQTT. So let's take a look at our agenda for today's tutorial. We're going to give an introduction to Industry 4.0 and IIoT, but our focus for today will be more on practical protocols, which is MQTT and MQTT Sparkplug. We're going to define what they are and give some of the history behind them. We're going to talk a lot about how MQTT works, and we're going to discuss the implementation of MQTT in the OCS. We will also go through the configuration of MQTT in Cscape, and at the end we'll be going through your questions and answers. So let's take a look at Industry 4.0 and IIoT. Industry 4.0 is named 4.0 as it is considered to be the fourth industrial revolution. The first was the mechanization of water and steam. The second, the mass production and assembly using electricity. Third, the adoption of computers and automation. And the fourth is the smart and autonomous systems fueled by data and machine learning. The fourth revolution can be described as smart machines that get smarter as they gain access to more data that can be analyzed and is analyzed for them. The product of this is factories becoming more productive and less wasteful. The key feature or backbone of the fourth revolution is a network of machines, digitally connected and sharing information. In other words, the Industrial Internet of Things, IIoT. Machines have been sharing information for years now. For example, SCADA packages have been around a long time. So what differentiates them from IIoT? There are key features that do this. The huge increase in scale of connectivity between devices. The potential for data to be uploaded to the cloud. The much larger scope of analysis and potential for a feedback loop. These factors combined require new approaches to connectivity. The approaches we've taken to communications in the past, which are still viable for most factory environments today, may not be viable for scaling up the data acquisition and data reporting which is desired for IIoT. Before we take a look at MQTT, I would like to talk a little bit about Horner's own IIoT strategy statement, as we've been asked a lot about this recently. We will continue to enable and support you, our customers, with machine connectivity with the protocols that we have been supporting that are still viable, like the Modbus TCP, Ethernet IP, and other industrial protocol data. We're going to continue to develop and enhance WebMI, which is essentially the visualization aspect of reporting data, as that has become an important feature of our products. For IIoT, we're developing specific protocols that address the movement to get more machines reporting data through the implementation of REST, MQTT, which we are covering today, and OPC UA, which is definitely on our roadmap. Again, we will adjust our strategy appropriately as new solutions become viable and demand grows for them on the marketplace. Now we're going to talk about what MQTT is and how we're applying it. MQTT stands for Message Queuing Telemetry Transport, and it is one of the new approaches to connectivity demanded with the increase of machines coming online, reporting more data. It is based on the publisher-subscriber model and not a traditional poll response approach. Traditionally in factories, we would typically have a client or master polling multiple servers or slaves requesting data from each constantly, which would be done on a round-robin basis. This is typically inefficient, but you can always tell relatively quickly if a device you're trying to pull is not available. This method does not efficiently use bandwidth. For instance, a master could be querying a slave for its temperature data, and that slave could be reporting back the same data over and over again with no changes. The publisher-subscriber approach is more of a report by execution or a push approach, where the device that has the data is not being polled, but it's pushing data at an appropriate time. For example, when it changes or at a certain time. This allows more devices to share the same bandwidth with greater efficiency, and because of the way MQTT is designed, it works better with both reliable and unreliable network infrastructures. An example of a reliable infrastructure would be a hardwired Ethernet connection with high bandwidth, where an example of an unreliable infrastructure would be a low bandwidth Ethernet connection in a noisy factory. MQTT started out as a proprietary protocol and was created over 20 years ago. It was originally used to get data from oil fields in unideal communication networks and was released for standardization in 2010. MQTT as a protocol doesn't actually define everything required for two devices to communicate effectively. This is because it was created so that it would be generic or flexible enough to be used by different companies and different applications. MQTT Sparkplug was a profile that was created to fill in some of the gaps that MQTT by itself had, to allow devices have everything necessary to communicate together. Topic namespace was one of the gaps filled by Sparkplug. This is how data that's reported is organized in a hierarchy, which makes it easier to find. State management is another, which is a way of definitively establishing whether a device is offline or not. Because if you're reporting data on an exception basis, you have to have some way of knowing that the node that's reporting the data is online and healthy. And finally, the payload, which defines the format of the data that can be sent. MQTT's payload is binary data, meaning it can be almost anything, but there has to be a method to define what it is and what format it's in. So now let's talk about how MQTT works. So let's take a look at the publisher-subscriber model, which is used in MQTT instead of the client-server approach. An interesting thing about this model is that the publisher and subscriber never actually talk to each other, but they communicate through a broker, which is sometimes called a server. So, devices that are publishing data are publishing it to a broker, and devices that are subscribing to data subscribe to a broker. The data that's published is called a topic, and it is published at an appropriate rate based on the application. The role of the broker is to keep track of all published topics and distribute them to the subscribers, and when any connections are lost, the role of the broker is to notify any subscribers that the data is stale or the connection has been lost. Some facts about MQTT. It's almost always built on a TCP IP. It supports optional encryption via TLS. Brokers in MQTT are often called servers, and publishers and subscribers are often listed as clients. Clients may be publishers, subscribers, or both, as they don't have to strictly be one or the other. Now let's talk a little bit about MQTT Sparkplug, particularly nodes and devices. In Sparkplug, a node communicates directly on the MQTT network, so it communicates directly with the brokers. Sparkplug also has devices which communicates through nodes, so you can think of a node like a gateway, where a device is much less sophisticated like a sensor, which isn't high level enough to report its data directly. The OCS, or Operator Control Station, can support both node and device data. So now we're going to go through configuring our Edge of Network node, or OCS. First, we have to define our client ID. This is a string that must be unique. We recommend that you use your MAC ID as your client ID, as it is always guaranteed to be unique, because a MAC ID is supplied for every individual OCS, and it is tied to the LAN 1 port. There's also an ID that's tied to the LAN 2 port for the OCSs that has two LANs, but the serial port of the OCS is always considered its LAN 1 address. You must also define a group ID. This is very useful as it gives you the opportunity to logically group your nodes together. For example, you might have a plant 5, that is a series of controllers that are going to be reporting data. So you could create a group ID called plant_5, which could be shared by multiple OCSs in that plant. Lastly, we have the node ID itself, which is the text string that should have an easy to use name, as you're not going to memorize MAC addresses. An example of a good node ID is line3_OCS, as that tells you it's the OCS that's running line 3. It should be relatively short as it's going to be broadcast with every message. So these are the three items that we have to define when we're configuring our Edge of Network node. As we're establishing a connection over MQTT, there are a couple of things that happen. The first step is the node has to log into the broker, so we'll have to know the username and password, as this ensures only certain devices can gain access. During the process, the broker will effectively be running on a computer over Ethernet. The next thing that's defined is whether it will be a clean session or not. A clean session is a non-persistent connection, meaning if messages are missed, they're not stored in the broker, but are lost forever. In a not clean session, there is a persistent connection, meaning all missed messages are stored in the broker. Another thing you must specify when establishing a connection is a keep alive. A keep alive is a period of time in seconds where you're going to ensure that the node is communicating with the broker, so that the broker knows that the node is healthy. So if you, for example, set the keep alive to 30 seconds, it would check every 30 seconds to make sure that it's still communicating with the broker. And if the timer expires, it's going to inform any subscribers that are interested in said data that it is stale or that the connection is lost. The first thing that happens immediately after a connection is established is that birth certificate is sent to the broker from the node. This conveys that the node is ready to provide real-time data, and if the connection is lost, it contains data that will then be passed to a death certificate from the broker to any subscribing nodes to let them know that this data is unavailable and that this node is offline. Once a connection is established, you're ready to publish data. An OCS in MQTT is primarily used to publish data to a broker and not subscribe to a broker, although it can. It is primarily used to publish data because Industry 4.0 is all about machines reporting their data. So now we'll take a look at the process of publishing data. First of all, the data is organized in a hierarchy, which includes the details that I spoke about in a previous slide: client ID, group ID, and node ID. Optionally, some data could be reported as device data, and if you do so, you have to specify it as device ID. The next level is the topic level. A topic is a simple string, which looks like a path to access a file. It effectively defines, through a series of forward slashes and folder names, where the data is located. The final level are metrics. Those are the variable names along with the data type. So an integer, double, real, etc. The variable names are basically the metrics for the lowest level of data, and they can be a mix and match of different types. What you end up with when you combine your group ID, node ID, topic, and metrics is very well organized data, which defines the path for finding any particular variable within a node in a very organized fashion. We'll talk more about this later, but when data is published is decided strictly by the node publishing said data. With the OCS, we can decide to publish data on a periodic basis, on a trigger, on a change of state, etc. Next, we must define the quality of service. The quality of service is a very important part of our data publishing process, and it is specified by the node and not the broker. So when the OCS publishes data, it's not only going to define the topics and metrics, but also the quality of service for that particular topic. Now let's go through the 3 levels of quality of service in data publishing. Quality of service level 0 means that the data is only going to be published at most once, and there's no guarantee of delivery. We may be reporting data every 5 seconds, so any one message may not get through. Level 0 is the most efficient, but also the riskiest. Quality of service level 1 means that the data is getting sent at least once, and there is a guarantee of delivery as it keeps trying until the message gets through to the broker, although it is possible that duplicate data could be sent. In some applications, this can be disastrous. In others, it may not matter. Quality of service level 2 means data is going to get through exactly once, and it exists because of how disastrous it is for some systems to receive duplicate data. Level 2 is by far the least efficient level, and it has the most amount of steps involved. You would use level 0 if you have a stable connection and don't mind losing a few messages. You would use level 1 if you need to get every message and getting duplicates is not an issue. You would use level 2 if you need to get every message, but your system can't handle duplicates. Also, if a persistent session has been specified, then queuing of lost messages is supported in quality of service 1 and 2. Next, when publishing data, we must define a retain flag. If the retain flag is set when we publish the data, the broker will save the last good value and quality of service for that topic. The use of the retain flag comes in, for example, if there was a new subscriber to the topic. If you don't have the retain flag set, then the subscriber is going to have to wait till the next broadcast before it finds out what the data looks like. If the retain flag has been set, then the last good value will be sitting at the broker, and when a new subscriber comes in, it will immediately have information about the type of data it will be handling. There are a few things that happen during the publishing that don't have to be configured. For example, every time new data is published, a unique packet identifier is sent automatically. This becomes important when message sequencing is a big deal. Also, whenever the transmission retries, a duplicate flag will be sent automatically. Next, we're going to take a look at subscribing to data. Subscribing to data is a much simpler process than publishing. To subscribe to data, all a node has to do is send a list of subscriptions that they want to subscribe to the broker, as well as the quality of service level for each of those topics. The quality of service can be different from the subscriber to the publisher, as they both decide the quality of service based on their own network bandwidth and communication situation, so the broker never actually weighs in on that decision. At runtime, publishers establish a connection with their broker and start pushing data. Data is published by the publisher either periodically or on a trigger. Keep alive messages are sent as necessary by the publishers to ensure that the connection is still current. Any subscribers who want to subscribe to a topic provide a list of topics with their quality of service to the broker. Brokers receive published topics and pass them to subscribers. If the publisher-broker connection is lost, the broker sends a notification to all subscribers of the affected topics. So, that's effectively the whole process working. There's quite a bit of definition at the beginning of the process, but once it's done, you have quite an efficient process in place. Here's a graphic of a test that I've set up in my office. Apologies if it's a bit of an eye strain. So I set up an XL4, as you can see at the bottom of my screen, with the IP address 172.27.166. It's set up as an MQTT node, but it has both node data and device data, because I simulated having another device connected to the OCS. You can see the node data being published on the left and the device data being published on the right. So the OCS is communicating this data to the MQTT broker, this particular one being a Chariot MQTT broker, which is available from Sears Logic, who are common suppliers of MQTT Sparkplug brokers. I ran the Chariot MQTT broker on a Boon 2 virtual machine for testing purposes. As a test, I ran a demo of a product called Ignition SCADA, which is an internet SCADA system that uses MQTT as one of the ways of subscribing to data. The demo then displayed on the SCADA screen on the right. To the right of the SCADA screen, you can see, although it may be a bit small, the hierarchy or view that would be in the Ignition package as it was effectively browsing for topics. This hierarchy exists at a group level, node level, device level, topic level, and metric level. It's like a series of folders that are well defined and organized. What we're really looking at here is an OCS publishing data to a broker, and whichever devices are interested in that data can subscribe to that information. Okay, so now let's talk about the implementation of MQTT in the OCS. We're adding Sparkplug support in Cscape 9.9 Service Pack 3. It will be supported by all operating systems which are based off of Linux, and there's a list here for reference. There will also be a firmware update required to 1540. Okay, so the OCS is an MQTT Edge of Network node that supports both node data and device data. It can both publish and subscribe to data. The OCS can support a significant number of topics and metrics. It can connect up to 8 brokers. It can publish up to 64 topics, and within each of those topics it can have 64 metrics. Also, for each of those topics, you can decide whether you want to publish that data on a periodic basis, a triggered basis, change of state basis, or change of value basis. Okay, so now let's go ahead and do a Cscape demonstration of what we learned so far. Okay, so before we begin, I'm doing this demonstration in Cscape 9.9 Service Pack 3 with register-based advanced ladder enabled, and I'm running the 15.40 firmware update. First, we need to configure our hardware. To do this, go to the top right of your screen to the hardware configuration icon. You'll need to configure your hardware so that it supports one of the OCSs that supports MQTT. So that, for example, is the XL series. In my case, I have the XL4 Model 2. So let's begin. Go to the top left of your screen, click Program, scroll down, click Messaging, go across and double select MQTT. Sparkplug is the first of what will probably be many selectable profiles of MQTT that we will be supporting, and for now we have no choice but to select Sparkplug. The next step is to configure the controller level, and you get there by selecting the tab option up along the top of the MQTT configuration screen. The first thing we have to do is define a bank of status registers, which must be 26 words long. This is where you're going to be fed back information, such as the health of the broker, how many messages have been successfully published, the connection status of each of the brokers, etc. There's an enable bit, which is a Boolean variable, which has been turned on in order for MQTT communications to begin. Next, we get to start seeing some of the stuff we talked about earlier, such as the client ID, which must be unique. And as we suggested earlier, you could use this button here to automatically use your own device's MAC address as your client ID, as there's no doubt that it would be unique. The other ID, node ID, is an English readable text. This is the one which you would name something like line3_OCS, meaning this is the OCS that's running on line 3, and there's no fear in anyone overriding this. Associated with my nodes could be a group of nodes, and in this example I'm using plant_5. So again, in our hierarchy, group ID is above node ID, meaning line3_OCS belongs in group plant_5. So, for example, there might be a dozen OCSs in plant 5, or even just a dozen MQTT nodes in plant 5 in general, as it doesn't have to be an OCS. There's also a button here to check whether your MQTT license is valid. There's one last field here called UUID, which is not used very frequently, but it can't be left blank. Okay, so we've defined the controller level. Now let's move to the broker connection. To do this, go here along the top of the MQTT configuration screen. Okay, so we start off with a blank state, with no brokers connected. We're going to take a look at a broker that I predefined. So I'm going to click it and select Edit. First, you need to give it a name, which should be easy to remember. In this example, mine is called HQ_broker, meaning this is the broker from headquarters, which we're going to publish our data to. Our broker type is fixed as Sparkplug. The broker IP is the address we use to access our broker over Ethernet. We can either hardcode the IP address or the URL here, or we could assign a variable to it and populate the variable at runtime. For example, the OCS touchscreen. For this example, I've hardcoded it. The port needs to be 1883, and these are the user login credentials for the broker, which you always have to establish that this is a legitimate connection. Next, we have the keep alive time, which lets the broker know that the node is healthy and that the published data can be trusted. For this example, I've set the keep alive to 30 seconds. So this means that this OCS has to communicate with the device at least every 30 seconds through a heartbeat message. If I'm regularly sending data every 5 seconds, I won't have to send that heartbeat signal because I'm sending data within a shorter span of time than the 30 seconds. The option for a clean session is also selectable. A clean session is when the broker doesn't keep track of or store missed messages in its local memory. If you don't select a clean session, missed messages are stored. So those are the settings at the broker level. You can also go to the encryption tab across the top and enable the typical SSL TLS encryption, but in this example I won't be enabling it. Okay, so now we've defined a connection with the broker. Next, we need to define the topics. Remember, in our hierarchy we have group ID, node ID, and sometimes device ID. And then we have the next level, which is topic. And you can think of topic as a folder with a series of variables which are called metrics. Okay, so in this example, I previously created a single topic, HQ_broker. So I'm going to double click to examine it. Now, we have to determine which broker that this topic is tied to, but we only have one broker here anyway. This prefix, process, is essentially the topic name. These names can go multiple levels deep with slashes. For example, process/tempcontrol/PID. Next, we have to decide, are we publishing or subscribing to data? And what is our quality of service level? As it ranges from 0 to 2. 0 sends just once, 1 sends at least once, and 2 sends only once. So as you can see, I've selected quality of service 0, because I'm sending data periodically every 5 seconds, so losing data probably isn't too much of an issue. What I skipped over here are the metrics, or the variables that are being reported as a part of the topic. In this example, I only have 2, but there could be up to 64. So, I have pressure, that's type integer, and temperature, that's type real. If I click on these, you'll see that I'm using a traditional register-based version of Cscape. I've defined this variable IO, named as pressure, for this A1. And I've defined the variable IO name as temperature for this R720. Okay, so now that we've defined that these metrics are a part of this topic, we also must decide when we want to publish the data. We could publish the data on a periodic basis, on a trigger, on a change of state, or a change of value. So again, we can report up to 64 metrics per topic and can publish 64 topics. So we can report quite a bit of data. And if we're to subscribe to this data, it would be a similar process, just simpler. Okay, so that is how you configure MQTT in Cscape 9.9 Service Pack 3.